Sometimes a polynomial equation with all real coefficients can have imaginary roots. So that means that a matrix with real entries can have imaginary eigenvalues, and those are going to lead to imaginary eigenvectors. But the good news is that imaginary eigenvalues come in pairs, and that's going to save us some computation. Now we have a conjugation map on complex numbers that takes a plus bi and changes it to a minus bi. So we usually write a line over the number to denote complex combinations. So complex conjugation. So a plus bi conjugate is a minus bi. We keep the real number the same, and then the imaginary part switches signs. Now, complex conjugation is linear. So if we have a plus bi plus c plus di, we conjugate the whole thing. That's just like conjugating the parts separately. So we can conjugate a plus bi and c plus di separately and get a minus bi plus c minus di. Now, complex conjugation has a property that linear maps don't have, and that is it respects multiplication. So that property means that if we take complex conjugate of matrix entries and multiply the matrices, we can do it in either order. So we have the consequence. So if we have a product of matrices A, B, and we take the complex conjugate, it turns out to be conjugate of A times conjugate of B. I won't prove this, but the details are pretty straightforward if you want to try it. And then a consequence of that fact is let's suppose that lambda is an imaginary eigenvalue of A. Then AV equals lambda V, so V is an eigenvector. With eigenvalue lambda. So AV being equal to lambda V implies that we can take the conjugate of both sides. AV bar equals lambda V bar. And that implies that A bar V bar equals lambda bar V bar. Now, if A is real, then conjugating a real number doesn't do anything. So A bar is just A. So that means that A V bar equals lambda bar V bar. So in other words, if V is an imaginary eigenvector with imaginary eigenvalue lambda, then the complex conjugate of V is an eigenvector also. And we can see from this equation what its eigenvalue is. It's lambda bar. So once we do the work to find an eigenvector V and its eigenvalue lambda, these are imaginary. We can just take complex conjugates and we get another eigenvector and another eigenvalue. So let's do an example of that. Let's let A be the matrix 1, -3, 3, 1. So to find the eigenvalues, we'll solve determinant of A minus lambda I equals 0. So determinant of A minus lambda I is determinant of 1 minus lambda, -3, 3, 1 minus lambda. That equals 0. And that is, determinant is going to be 1 minus lambda squared minus -9 plus 9 equals 0. And that means that, so we've got lambda squared minus 2 lambda plus 1 plus 9 equals 0. And that means that lambda squared minus 2 lambda plus 10 equals 0. All right, then if we use the quadratic formula, let's see what values of lambda satisfy that equation. Lambda is going to be one of the numbers -b plus or minus square root of b squared minus 4ac minus 40 all over 2a. So we've got 1 plus or minus square root of -36 over 2. That is, lambda is one of the numbers 1 plus or minus square root of 36 is 6, so we've got 6i over 2, which is 3i. 1 plus or minus 3i. So two imaginary eigenvalues. All right, so to find the eigenvectors, let's say for 1 plus 3i first, solve A minus 1 plus 3i identity matrix V equals 0. So what does that look like? Our matrix is 1, -3, 3, 1. I'll put that up here. 1, -3, 3, 1. So if we subtract 1 plus 3i from the diagonal entries, we get 1 minus 1 plus 3i, 1 minus 1 plus 3i, -3, 3. And this matrix is 1 minus 1 is 0, so we've got minus 3i, and then minus 3, 3, 1 minus 1 is 0, so minus 3i. V1, V2 equals 0, 0. All right, let's use some row operations to make this a little simpler. So let's write the augmented matrix negative 3i, negative 3, 0, 3, negative 3i, 0. Let's divide everything by 3 so that we get negative I, negative 1, 0, 1, negative I, 0. And then let's put this 1 up in the 1, 1 position and swap rows to do that. So 1 swap with 2, and we've got 1, negative I, 0, negative I, negative 1, 0. And then to get rid of the negative I here, let's add I times the first row to the second row. So row 2 becomes row 2 plus row 2 plus I times row 1. So then we get row 1 is still 1, negative I, 0. Row 2 becomes negative I plus I is 0. Negative 1 plus I times negative I. Negative 1 plus I times negative I. 0, 0. And what's this? Negative 1 minus I squared. I squared is negative 1, so this is negative 1 plus 1, so that's 0. So the second row is just 0 plus 0 equals 0. So we only need to worry about the first one. So we've got the second row goes away. So the first row says that V1, that should be an I there that I didn't copy right. V1 minus I, V2 equals 0. Or in other words, V1 equals I times V2. So the 1 plus 3i eigenspace is all the vectors of the form the first component equals I times the second component. So t and it, where t is any real number. And one basis is, well, if we let t be 1, I 1. Now 1 minus 3i is the other eigenvalue. And the 1 minus 3i eigenspace equals, same as this except we put a minus sign everywhere there's an I. So minus I t. T varies over all real numbers. So one basis is negative I 1. So the procedure for finding complex eigenvalues is exactly the same. We solve the same equation. And then when it comes to finding the eigenvectors, we get a little bit of a shortcut, because as soon as we find one, we can just put minus signs in front of all the i's. That is, take the complex conjugate, and we get the other eigenvector for the other eigenvalue. The end.